on gravity. And I know, just for whatever it's worth, in the proceedings, I put a little table of contents, I think, on the page 4, and listed things by topic. And by far, this year, the #1 topic was gravity. So I imagine everybody's interested in this. We're all trying to figure out what the heck is it. And Bob DeHilster is going to be having a meeting here tonight on gravity. So be sure to come here if you're interested in that. That'll be in what's the room again?
Rio Grande.
The Rio Grande room. So be there for that if that's your thing. And be here tonight if you're interested in structure. So our first speaker this afternoon is going to be Dr. Ralph Sansbury, who joined us for the first time in Storrs, Connecticut, but he's been active in dissident physics for, my goodness, 30 years or more, right? And he's been developing, I think, a really interesting idea of dipoles as the cause for a lot of forces, and gravity in one of them. And he's going to be talking about 2 related talks. Tomorrow talking about light, and today talking about gravity, that are related to each other, both stemming from the same idea of the dipole action. So, we're Dr. Ralph Sansbury.
Hello, I'm going to talk about the similarity between the magnetic and gravitational fields and this underlying electric dipole mechanism to explain them. I hope to show you the magnetic and gravitational fields of stars, planets, and satellites are attributable to electric dipoles in their atoms, ions, and atomic nuclei transverse to their spinning orbital motions. Thus, for the Earth, collinear electric dipoles are produced along each radial line and along each line of longitude that are perpendicular to the force, the tangential force associated with the spinning orbital motion of the astronomical body. These dipoles are produced by this changing tangential force, mechanical force, but ultimately all forces are electric, as we all know. So these forces act on a minuscule charged particles circling inside each nuclear core at superluminal speeds, creating a sustained elliptical displacement of centers of charge, starting with 10 to the minus 15 radius nuclear diameter, and same for the free electron, and we're talking about conductors. And this sustained displacement, elliptical displacement of centers of charge produces the dipoles. The counterclockwise eastward spin of the Earth and the minuscule charged particles inside these nuclei and free electrons implies that the positive poles of the radial dipoles are pointing outward to the surface, and the inner poles are negative, pointing toward the center. And this is very interesting because it explains the negative charge on the surface of the Earth, which leads to a potential difference of 100 volts per meter up to the top of the stratosphere, which is 400,000 volts. And this is sustained, and this electric charge is held by these positive poles of these electric dipoles associated with the spinning and orbiting motion of the Earth. Same thing is true for the Sun. Similar thing is true for the Sun. Okay, now, let's see if I can operate here.
I'm not sure if you're going to be able to change the slides. This is a PDF file. So I can change it.
Oh, there. Oh, sorry. Okay, there it is. Okay. So the first slide shows the repulsion of parallel dipoles, which is then half as great as the attraction of the collinear dipoles. So you get a sense of what these dipoles are and what their specific mathematical forces are. Now, I have to keep this all in mind. I can always come back to it. The second slide shows how the ellipse inside the nucleus, the 10 to the minus 15 radius nucleus, is formed from, and the free electron, is formed from a sustained electric field E in current-carrying wires, acting on this small particle of charge minus E in the case of the nucleus, and minus 2e in the case of the free electron. That is, the electron, I'm saying, has a charge of plus e in the center, which contains most of the mass, 10 to the minus 30 kilograms, and the outer part is of charge minus 2e, And and the mass we're going to find out later is only 10 to the minus 55 kilograms. And that's implied by what we observed about the magnetic force and representing it as caused by electric dipoles. Anyway, I'm getting a little ahead of myself. Okay, so this slide shows how the ellipse inside the nucleus is formed from the sustained field, the electric field E, and how the ellipse eccentricity is 1 minus the eccentricity times the radius, the eccentricity times the radius, the circular radius, divided by 1 minus the eccentricity, and that gives the dipole produced by this elliptization of an originally circular motion. Now the equation, is this point to the equation? No, sorry. Whoops. Oh, this is the equation here is the magnetic force between short current carrying elements according to Ampere's formulation of the magnetic force, which is equivalent to the common B/R formulation, and you can derive it. But this is an inverse square force for a very short current carrying segments of wire. I call them elements. And now we make this equal to an electric dipole force on the right-hand side, where you have now the 9 times 10 to the 9th as the electric coefficient instead of 10 to the minus 7. But you multiply that times n, which is 10 to the 18th, meaning the number of the number of atoms, 10 to the 28 atoms per cubic meter for copper, times the charge times the cross-section area A, times the distance r between two parallel wires, times v, the drift velocity of the free electron in the current carrying wire, over c. Now NEAV is the current, is equal to I. On the next slide, we show that with a 1 amp, that what we have here, this is a 1 amp current. NAEV is the current, and then okay, so that's clear. Okay, now the numbers. Whoops, sorry, going the other direction. The numbers are over here. So this one, everything cancels except this, and we see. And then we can solve this 8.47 times 10 to the 28 is the number of atoms, and the 3.14 times refers to the cross-section area times 10 to the minus 6. 1.6 refers to the coefficient of the electron. 1.602 times 10 to the minus 19 is the charge of the electron, and this times the drift velocity of the electron then is equal to 1. And that's equal to 4.26 times 10 to the 4th v sub b. We get v sub b equals about 10 to the minus 5 meters per second for this 1 amp current in this wire of very low, not much resistance. Okay. Now, this, and then we can continue to solve for the electric field associated with this current of 1 amp. And this drift velocity of 10 to the minus 5 amps, and it's about 10 to the minus 3 or 10 to the minus 2 volts per meter. Okay, now the problem is to create an elliptical displacement of charge inside the nucleus with this tiny 10 to the minus 3 volt field, which times the electron gives you a 10 to the 22 Newton force on the orbiting charge of the free electron and the nucleus. And how do you, so the mass has to be very small to make this possible. And we find that the velocity increase, v1 minus v sub 0, where is this one? So this is the increase in velocity of this orbiting mass due to this very weak outside force against the very strong central force that then produces this this ellipse. And we have what is the effect going to be? Well, we don't know the mass yet, but we can solve for the mass, and that mass then is 10 to the minus 28. Well, that's the square root of it. So we end up with something that is 10 to the minus 55th as the implied mass. This tiny particle, we found a particle smaller than the neutrino that they found at CERN with billions of dollars just by going through this mathematics and applying it to very simple force between two parallel wires, each carrying 1 amp. So I think this is a very important result for now understanding the electric dipoles in dielectrics. But can such dipoles be produced inside dielectrics? Yes, if the field is constantly changing, is constantly repeated to oppose any redistribution of charge of the loosely bound orbital electrons in the dielectric. And how do we know this? Well, a magnetized steel needle lining up with the Earth's lines of longitude and dipping towards the Earth along lines of radii from the surface to the center of the Earth shows this quite well. It's not exact because the magnetic field of the Earth is slightly, magnetic North Pole is different than the physical North Pole. Now we all know using a compass that sometimes if you get near some steel, your compass is going to be thrown off. So we have a non-uniform distribution of iron in the Earth that's throwing off this measurement of the gravitational field. But the gravitational field and the magnetic field are the same. And so that's the basic idea of this. Now, note the orbiting electrons in iron atoms, how these magnets work. In the outer shell, or in the one of the inner shells, cross the path of electrons orbiting the outer shell and reverse the spin of these electrons. And the spin is essentially the electric dipole. And these spins and electric dipoles are, one is in one direction and the one on the other side of the atom is in the other direction, and in general they balance out if there are an even number of electrons in the outer shell, in the outer ring and outer shell. But in some cases, it's not an even number, and in this case, a whole bunch of them are going to be in the same direction. That's true for iron, cobalt, and nickel, and maybe a few other things. And so this is what gives, ultimately, this magnetic property that we can measure the magnetic field and gravitational field of the Earth. Okay, now let's go on to the next slide. Next slide. Next slide. Is this the next slide? No. This is the next slide. No? Okay. There. No. Okay. Oh, no. And I'm going to skip this. I don't have time for all this. Okay, now if the Earth was all silicon, then read this. Okay, I can read it on here. Then this is how many kilograms divided by 28, how many moles of silicon are in the Earth, and we multiply that times 10 to the 28, and then we multiply that times Avogadro's constant, 6 times 10 to the 26, and this tells us how many protons and neutrons there are on the Earth, and no matter what we do, the way you can see how this is done, no matter what it's made of, silicon or oxygen or the average, whatever it is, that's going to be the number of electric dipoles if there's one electron dipole per neutron or proton. Now the force between dipoles of length, the radius of the Earth in this case, times some unknown, concentrated at a point about 10 to the 6 meters from the surface and acting on a single dipole on the surface of the Earth is this formula here. So here now we have this electric representation of this gravitational force, and when we set that equal to for the gravitational force according to Newton, we get this expression for the dipole for this value s, and then we multiply that r sub e times s. Let's go on to the next slide. Oops. And then we get about 10 to the minus 12 meters as the average dipole length of each proton and neutron required for this collinear dipole force to work between a proton on the surface and a ring of dipoles concentrated at the center of the Earth, representing really the total force, the superposition of all the forces of all the dipoles and all the atoms of the Earth, projected on the proper line, and taking all that into account. And this is what we get for the dipole. And this is reasonable. It's not, it's small enough. Now, if it's more than 10 to the minus 11 meters, the dipole, we'll see that it's really smaller than that. But if it's 10 to the minus 11 meters, the inner shell of electrons will prevent it from getting so big. So when we're talking about dipoles in magnetic parallel current carrying wires, or as part of gravity, all these dipoles are very small and within the size of the nucleus, 10 to the minus 15 meters, and certainly not more than 10 to the minus 11 meters. Okay, so now can we do the same thing for the sun? The sun's effect on the Earth, the gravitational effect on the Earth. Yes, we can do the same thing for the sun. And here's the electric dipole force for the sun, and we have here S sub E is this unknown for the sun, and for the Earth, which we know is now, let's say, is 10 to the minus 11, and S sub S is this unknown for the sun. And if we assume that the S sub E is 10 to the minus 11 for the Earth, then we get this value for the sun, which is, well, it's not very big, so it's 10 to the minus 4. I mean, it's not very good at all. But if we consider that the protons and the neutrons are made up of smaller particles to which the same kind of force is acting and the same kind of dipoles are being produced, we have about 718, you could say, positrons and 718 neutrons to get to the total number of positrons and electrons that would add up to a neutron or a proton. We know that because the electron-proton ratio is 18. It's about 10 to 1,000, 10 to the minus 3, 1813 or something. So we have 10 to plus 3. So we have 10 cubed that we can add to all of this, and this will bring our R sub S sub E S down to 10 to the minus 10. And would that work for the sun? Well, the sun is a sort of unknown thing, and could you have dipoles of this sort within the atoms, within the nuclei of these ions in the high temperature sun? And maybe so, and maybe other things besides the nuclei are involved in producing these dipoles. So could it be done for the force between the sun and the galactic center, which is not just 10 to the 11 meters away, but it's 10 to the 20 meters away. And then so if we have 10 to the 20 times some little value s is going to produce times a certain number of whatever they are in the galactic center times this 10 to the 60th or whatever they are in the sun that will produce this force. So that is a good area for research and finding out more about the galactic center and finding out more about the sun. Now, I have the right page. Okay, so anyway, so what is the advantage of this representation of the of the gravitational field of the Earth. Well, it can explain a lot of things like seafloor spreading, the repulsion effects discovered by Dipoles in 1890s and Fischbach in 1986. There's slight repulsion effects in these gravitational experiments, and so you have the situation where longitudinal dipoles could also explain then seafloor spreading. So you have repulsion effects between pieces of the Earth, as well as attractive effects between pieces of the Earth. So that's one aspect of the thing. Now another aspect I think is the Hafele-Keating experiment in the 70s, which showed one plane taking off with cesium clocks going east, and one plane taking off going west, coming back to the Naval Observatory in Washington and comparing the times of the two clocks. The one going east came back with 300 nanoseconds slower. The one going west all the way around came back with 30 nanoseconds faster. And one way you can explain it in terms of this theory of gravity is what's happening is that when the plane is flying eastward, it's a little heavier. Dipoles are produced in there because of the motion of the plane, producing tangentially producing longitudinal and vertical dipoles, and the vertical dipoles are pulling more on the vertical dipoles in the Earth, so you're getting more of an attraction. And just the reverse happens when you go westward. So there are all these things that tie in with with such an explanation of gravity, and which Newtonian gravity doesn't explain, and Einsteinian gravity doesn't explain. Now, Einsteinian gravity, you say, well, how do you explain the bending of light by the sun? Well, the bending of light by the sun, instead of the sloping of space around the sun as the star-like photons supposedly come brushing by the sun to the sunny side of the Earth, it's a little bent when compared to what happens when you observe the star from the dark side of the Earth. Well, this could be because the electric gravity of the sun acting on the receiving photoreceptors on the Earth are causing a delay, and so the light from the star appears to be coming from a slightly bent direction than when this is observed from the dark side. So I talk more about that in the talk on light tomorrow, and that's all really for this now, unless there's some questions.
Questions?
It worked out great.
Yes.
Come to the mic, please.
7 minutes, yeah. We have 7 minutes.
Yes, I'm Bill Nichols, and I'm an atmospheric scientist, and I was very stimulated by reading your comments about the conclusion of how it affects the thermal fields and gravity of the Earth.
Right.
What I'm understanding you're saying, which I find commonality with from my experiences, is that if by definition this affects how the whole thermal field of the Earth atmosphere galactic system works, that the equations that we use and the problems we have in Earth atmosphere, and for example, how we define temperature, a mean temperature, it's a mean energy, and how we define energy, heat, and of course forms of energy, are inherently unbalanced. Is that correct? Which means the primitive equation, they're incomplete. Because we're using a mean, and we're using heat as a potential, just like you use an ocean, a gravity wave up and down. And if we're defining it in a different framework versus what I understand you're telling me, then temperature and heat, which we still don't fully understand, need to be re-examined. Is that correct? In terms of this context?
Yeah, I mean, the time between collisions is going to determine how these dipoles are produced. The hotter it is, the faster, the slower, the smaller time between collisions, thermal collisions, and that's going to affect what these dipoles are and what gravity is. Yes, yes, yes.
Okay, I find that very. I think there's commonality, so I'm encouraged by what your comments are. Thank you.
I'd be interested to find out more. Thank you.